Hello, hello. Hope I'm live. And oh, today I'm going to read the paper. Okay, what am I doing? Give me a sec. Yeah, today I'm going to read the paper towards monosemanticity, decomposing language model with dictionary learning. So this is the second part of this of reading this paper. Yeah, and yeah, just before I start, okay. So everything looks all right, and let's continue. Yeah. So in the first stream, like I skimmed over the whole paper, skimmed the whole thing. Uh, Today I'm going to read it as it is, like read like every line of it, at least as a plan. So this is the notes we made yesterday. We're going to write over it. Yeah, right. So towards monosemanticity, decomposing language model with dictionary learning. Use a sparse encoder. Using a sparse autoencoder, we extract a large number of interpretable features from a one-layer transformer. So the basic idea of this paper is that we make a one-layer transformer and use a sparse auto. Yeah, I think I should write that down. The key idea of this paper is to use a sparse autoencoder to uh, try to understand what each neuron in the MLP layer of a one layer transformer mean. Okay, the idea is that this I will learn dictionary of features that is more interpretable than neuron itself. Yeah. Users try to understand what each neuron on the MLP layer of a one layer transformer mean. Like what concept, like what vague concept does each neuron refer to? Right. That's the key idea of the paper. Right. Yeah, crucial lesson there. Mechanistic interpretability seeks to understand the neural network by breaking them into components that are more easily understood than the whole. By understanding the function of each component and how they interact, we hope to be able to reason about the behavior of the entire network. The first step in the program is to identify the correct component and analyze. Okay, so first we have to identify the correct component. I mean, to understand to do proper mechanistic interpretability tasks, right? Last check. All good. Unfortunately, the most natural computational unit of neural network, the neuron itself, turns out to be a natural unit for human understanding. Turns out not to be a natural unit of human understanding, obviously. This is because many neurons are polysemantic. They respond to a mixture of seemingly unrelated inputs. So we're going to take you and put you here. We use the psi to make them monosemantic. In the vision model inception V1, is this the one I read yesterday? Yeah, like I don't even remember reading any of this. Yeah, this is it. Weird, right? Unfortunately, the most natural computation unit of the neural network. Okay, sure. They correspond. Okay. In the vision model inception V1, a single neuron responds to a face of cats and fronts of cars. In a small language model we discuss in this paper. This is a paper. What I mean, the response is a mixture of academic citation, English dialogue, HTTP request, and Korean text. Polysemanticity makes it difficult to reason about the behavior of networks in terms of the activity of individual neurons. So, ideally, in an ideal world, we will make neural networks like monosemantic and still as efficient as it used to be, right? I kind of want to do this monosemanticity with a like GPT-2. Man, I really want to do that. One potential use of polysemanticity is superposition, a hypothesized phenomenon where a neural network represents more independent feature of the data than it has neurons by assigning each feature its own linear combination of neurons. Hmm. Yeah. So one feature, instead of referring to one specific neuron, it refers that feature is associated with multiple neurons, and the linear combination of those neurons would essentially mean this concept. If we view each feature x as a vector over the neurons, then a set of features form an incomplete linear basis for the activation of the neural network. In a previous paper, we show that the superposition can arise naturally during the course of neural network training. If the set of features useful to the model are sparse in the training data, as in compressed sensing, sparsity allows a model to disambiguate which combination of features produced by any given activation vector. Hmm. Okay. I kind of want to write those things too. Give me a sec. So, during training, uh, uh, during training of a neural network, hmm, the each feature is learned as a linear combination of neurons instead of each neuron corresponding to a feature. Yeah. Mm-hmm. The previous paper, we show that superposition can arise naturally during the course of neural network training. Use a set of features useful to the model as sparse in the training data. Okay, this can happen more if the data is sparse. Okay. As in compressed sensing, sparsity allows a model to disambiguate which combination of features produce any given activation vector. Hmm. Mm, In toy models of superposition, we describe three strategies for finding a sparse and interpretable set of features if they are indeed hidden by superposition. Creating model without superposition, perhaps by encouraging activation sparsity. Okay, this is what I was thinking actually. Like instead of making normal models, we can what give it to the loss function such that if more than one neurons are activated during training or inference, the loss is like more. Using dictionary learn to find an over complete feature basis in a model exhibiting superposition. I don't know what that means. Using dictionary learning to find an over complete feature basis in model exhibiting superposition. Probably this is what we are going to do. A hybrid approach relying on combination of the two. Explain, you know, when you will represent multiple features within the same set of activation. This can happen. This can make the model's internal representation harder to interpret. Yeah, creating model sparsity. Okay, using dictionary learning to overcome the feature basis. Find a more interpretable representation of features from the already trained model exhibiting superposition. Hmm. Hmm. Okay. Then we have hybrid approach. For decomposing a question into larger, more redundant set of basis vectors, it becomes easier to identify into the component features. This is probably what we're doing in this paper. Oh, this we are doing this. Okay, combining both these. Okay, cool. Since the publication of the work, we explored all three approaches. We eventually developed counterexamples to persuade us that the sparse architecture approach was insufficient to prevent polysemanticity. Really, okay. And the standard dictionary learning methods had significant issues with overfitting. Okay, this is kind of cool sentence. In this paper, the goal of this paper is to provide a detailed demonstration on the sparse organ order, compellingly succeeding at the goal of extracting interpretable feature from superposition. and enabling basic circuit analysis. Okay, concurrently, we take one line transformer with a 512 neuron MLP layer and we decompose the MLP layer into a relatively interpretable feature by training sparse autoencoder on MLP activation from an 8 billion data point. Oh, they take 8 billion data points. With expansion of with an expansion factors ranging from this to this. We focus on detailed interpretability analysis on those 4096 features in one run which we call A1. In global analysis, we argue that the typical feature is interpretable and they explain non-trivial portion of the ML pillar. Finally, okay, this is talking about the future steps. We also provide three comprehensive visualization of the feature. First of all, features from 90 learned dictionaries. We, we present activating data set examples and downstream logic effects. We recommend the reader to begin with the visualization of A1. Second, we provide a data view showing all features and combined for mm, mm, okay. Mm. Oh, I think they are referring to what each activation means. Oh, okay. This feature files for reference in scientific paper. Oh, okay, okay. You're explaining what each activation does. 500 features. Okay. That's nice. Fast auto encoder extracts relatively monosemantic feature. We provide four different lines of evidence. Find a specific context for which we construct computational proxies. Human analysis for large random sample of features. Automated interpretability analysis of activation for the features learned by the autoencoder. And finally, automated interpretability analysis. Where the last three analyses show that the most learned feature are interpretable. I don't claim that the interpretation catch all aspects. Investment is a neuron basis. We find the features. So not active on any top data set. Okay. Relatively universal. It's probably because data sets are like what human features appear to split as we increase atom corner size. True. Just 512 neuron can represent 10,000 features, tens of thousands of features. Yeah, I mean, it's like 2 raised to 512 possibilities, right? Basically. Yeah, that's a huge number. That's certainly more than all the, what do you call it, possible features. Certainly. Or less class. Features connecting finite state automated like system that we implement complex behavior to problem setter. Okay, before reading problem setter, I think I'll take a small break. Give me a sec. Yeah, we'll continue a bit later. I think I have a, yeah, bit later.